Hello everyone, welcome you all to TechnoBiz, and today we have a session with reference to the Executive Diploma 360 degrees on rubber industry, technology and management. As part of this diploma program, our participants have to make presentations based on their experience and expertise. And today I'm pleased to host Mr. Robert Edge. He's a development technician at the Fluid Compounders based in UK. He's one of the participants of this Executive Diploma program. So he'll be giving a talk on the color matching of rubber compounds. So let's hear from him about what's all about color matching, why it is so important for the rubber compounders. Robert, over to you. And I invite you to give your talk. Yeah.
Thank you, Param, and thank you to TechnoBiz for giving me this opportunity to present about colour matching of rubber compounds, and also thank you to Fluid Compounders for giving me this opportunity on this course. It's been very good so far, a lot of information to take in, and hopefully I can share with you more about the colour matching of rubber compounds, which will go in depth of what colour matching means in the rubber compound, why we do it, and also how we do it. So with regards to Fluid Compounders, we are a trusted advisor to top engineering firms developing for BAE Systems as their award-winning compounder. We're also the key strategic supplier of choice of rubber processors, so no matter what industry you are in, we will give you a competitive advantage. We specialise in custom rubber compounds, providing unparalleled quality and technical advice since 1979. Fluid Compounders have over 40 years experience supplying quality compounds to a wide range of industries. We understand rubber in depth, from formulation to application, and supply the highest quality rubber compounds to meet the most demanding of end-user specifications in industries ranging from oil and gas to food processing. We also understand the needs of downstream processors, working closely with our customers to ensure the compounds we supply process efficiently, thus minimizing waste. We employ about 75 people here currently, and we have expertise from our technologists to our millmen, some of them with over 30 years experience, and they are invaluable to this company. So we'll talk a bit about colour matching of rubber compounds. So we'll start with what is colour. We live in a world rich in sensory experiences, which we are constantly sampling. Our visual system is an amazing tool, using our ability to detect both subtle and large colour differences. We process and discriminate millions of different colours. It is the basis for learning the shape, size, and arrangements of objects in our world, and we rely on it successfully to navigate our environments. Our perception of colour is not created at the moment of vision. Our experience of colour is created through the exchange of information between the eye and the brain. The brain receives the sensory input from the receptors in the eye and processes that information by applying a highly complex classification system. This is an instantaneous and ongoing process. So let's talk about colour versus appearance. The experience we call colour influences and is in turn influenced by other aspects of objects in our world. Texture, gloss, opacity, which is the look and feel of a surface, along with illumination, all contribute to the colour we perceive. However, we tend to separate those appearance attributes as being independent of the materials that colour an object. For example, one may change the appearance of a plastic cup by imposing a texture into its smooth surface. In some lighting conditions, a change can dramatically change the cup's colour. That mechanism is very different from creating a colour change by changing the recipe of the dyes or pigments used to make the plastic cup. The eye-brain combination is far superior to any instrument-computer interface. for integrating all of the visual information it receives. Instrumental color evaluation systems do not yet have the ability to accurately process color and appearance properties. However, they can precisely analyze the color of an object and have become invaluable tools in the specification, production, and inspection of commercial products. So as you can see with this picture on the right-hand side, we've got the same object, half of it with indoor light, half of it with natural light, and you can see the difference that it makes depending on what light source is used to the appearance of the color. One example would be a supermarket we have here in the UK called Asda. I believe they have 3 different colors for their sign, one for the outside, one for the inside, and also one under a different lighting near the fridges and refrigerators. This shows how the different color can affect what people perceive it as. So the color classifications. Scientists have run a variety of independent tests to determine if humans share an innate system for classifying colors. Each of these experiments provides the subject with a large sample of colors. Samples were similar in texture, but covered a wide range of colors. Despite the sample set used, a common set of organizing characteristics have appeared repeatedly in these experiments. All of these samples were organized by the observers based on 3 fundamental properties. So these properties are the dominant color, which is the hue, which we see here, which goes from red, orange, yellow, green, etc. The intensity of the colors, which is the chroma, which we see here, which you can see from how bright it can be to how dull a color can be. And then there's the lightness of the color, which we have here going from white down to black, and you can see how it affects what the color will look like. So if we talk about the hue describes what we commonly refer to as color. Although a perceived color is composed of multiple colors, it is typically concentrated within a particular range of the visible spectrum. This is the dominant color, like violet, blue, green, yellow, orange, red, purple, etc. Basic hues in the visible spectrum are graphically represented via a circle referred to as the color wheel, as we see on the right-hand side here. The chroma, now that describes the purity of a color. It is associated with the color intensity. A high chroma color produces an intense color, while low chroma color is perceived as a muted color. The words brighter and duller are commonly associated with this attribute. Chroma is independent of hue and is represented on the color wheel. As the chroma of the color increases, the location of the color moves towards the edge of the color wheel. So we can see when we have 0% saturation of how dull a color will be, and at 100% saturation, how bright the color will be. And to talk about the lightness, this locates the color along an overall lightness-darkness continuum, with white at the top and black at the bottom. It is a description of how much overall light is coming from the object. The lightness attribute is independent of hue and chroma, which, as you can see here, how it changes from darkness to light, and also the different backgrounds of how it can be perceived looking at the object on different objects as well. So the measurement techniques we use in colorimetry is the tristamulus colorimeter, and the spectral photometer. Currently in Clue Compounders, we have the spectral photometer, which we use on a daily basis for quality control as well as color matching a new compounds. So the tristamulus colorimeter is a colorimeter uses filters to record the amount of light reflected in 3 wavelengths ranging across the visible spectrum. It includes red, green, and blue filters that generally correspond to the 1931 CIE 2 degrees color matching functions X, Y, and Z. These uses simulate the detectors in the eye. The color matches represented by the filters depend on the physical light used. Because of this, a colorimeter can produce a tristamulus notation only for one light, which is the measurement light, and for one observer condition, which is simulated by the filters used for the instruments. Tristamulus colorimeters have a very short measurement times and simple to operate and relatively inexpensive. They are mainly used in quality control and reliable for evaluation of color differences and color tolerance checks. However, this colorimeter cannot detect metamerism and is not used to calculate color formulas. So like I said, this is the instrument that we have in Clue Compounders, which is the spectral photometer, and it analyzes the light reflected or transmitted by a sample at each wavelength in the visible spectrum, compared to that from a reference sample. So what we'll do is we'll scan in the sample of the color we're trying to match, which could be a RAL color or a Pantone color, and then we can then use that color to try and match what we mix into that. Or likewise, if we've got a established rubber that has the color that they want, then we can compare future compounds we create to that original color. They are fitted with a device, typically a diffracted element, which breaks the incident light into individual wavelengths. Spectral photometers measure the fraction of light reflected or transmitted by the object at each wavelength in the spectrum. This data represents the photometric characteristics of the sample. The resulting data are referred to as spectral data. So if we talk about spectral data, they're independent relative measurements of an object that serves as a fingerprint of the color. This data never changes for an object and can be used in several different ways. A single measurement of the object can be used to calculate the tristamulus values of a color for a variety of illuminant or observer conditions. Because it can project the tristamulus values for multiple illuminant or observer conditions, it can be used to identify whether samples are metameric to one another. The data can be used to evaluate color differences between samples and to calculate color recipes for a commercial color matching application. Spectral photometers are simple and fast to operate. Thanks to the technological developments, these instruments continue to become lighter in weight, making them portable. In addition, prices of industrial spectral photometers have become quite competitive with traditionally lower priced tristamulus colorimeters. So let's talk about why we color rubber. Colors in the rubber industry serve purpose beyond aesthetics. They contribute to branding, safety, product differentiation, process control, and customer appeal. By understanding the importance of different colors, manufacturers can leverage them effectively to meet customer expectations in the rubber industry, increase market share, and achieve a competitive edge. A few examples of this are product differentiation. Like in some cases, different colors are used to differentiate between product variations or specifications. For instance, in automotive manufacturing, rubber seals or gaskets of different colors may signify variations in material composition, performance characteristics, or size. Process monitoring and quality control. Colors can be used as indicators during the manufacturing process. By incorporating color-changing additive or pigments, manufacturers can monitor and control critical process parameters such as curing, mixing, or molding. Deviations in color can help identify potential issues and ensure consistent quality, which is another reason that we use our spectral photometer in fluid compounders. If a color comes through and it's not the same as the last one, something's gone wrong in the process, and we can look into why that is. So the factors that influence choosing the colored compounds. The primary reason why most rubber is black in color is the inclusion of carbon black as a common additive in rubber formulations. The main reason for using carbon black as a filler is the relative low cost, strength, UV protection, and conductivity. To achieve these properties from a filler system that uses mineral fillers, enabling the compound to be colored, the cost would be significantly larger using high-value materials like silica. Processing colored compounds can be problematic too, with dispersing large amounts of mineral and silica fillers being difficult. So let's talk about the polymer selection. The polymer selection plays a crucial role in the formulation and coloring of rubber compounds. Some key ways in which polymer selection affects colored rubbers are as follows. The compatibility. The different polymers have varying affinities for colorants, including pigments and dyes. The choice of polymer can impact the compatibility and dispersibility of colorants within the rubber matrix. Some polymers may have better compatibility with certain colorants, resulting in more uniform color dispersion and enhanced color stability. The transparency or opacity of a rubber compound can be influenced by the polymer selection. Some polymers, such as natural rubber or transparent elastomers like silicon, exhibit high transparency, allowing the colorants to show through with minimal interference. On the other hand, certain polymers or fillers may impart opacity to the rubber, affecting the final appearance of the colored compounds. And the chemical interaction. The polymers can interact chemically with colorants, which can impact color stability over time. Certain polymers may be more prone to chemical reactions with colorants, resulting in color shifts or degradation. Compatibility between the polymer and the colorant is important to ensure long-term color retention and to prevent unwanted changes. One of the reasons why this is important when choosing your polymer is if you're trying to color match the rubber to a certain color, you need to look at your base first, which is why we'll get a base formulation, cure that rubber, and it could vary anything from white to more of a brown color. Being more of a brown color can make it a bit more difficult to match that compound, as you're going to need to add more white, such as titania. The issue then with adding titania is you're going to impact the cure rate of that compound. So careful consideration needs to be used when choosing your formulation. So onto the pigment selection. We have organic pigments, which are carbon-based compounds that contain organic molecules. These are typically derived from coal tar, petroleum, or natural sources. These pigments consist of complex organic structures. And then we have inorganic pigments, which on the other hand are composed of mineral compounds that do not contain carbon. They are generally derived from minerals, ores, or synthetic sources. Inorganic pigments include metal oxides, sulfides, chromates, and other inorganic compounds. Pigments will come in two forms, master batch and powdered. The main difference between the two is the master batch pigments will be on a carrier and easier to use, but will be a lower concentration, usually around 20 to 80%. The powdered pigments will be much harder to use, but less cost due to the amount of pigment being used being lower. So what is a pigment master batch? Master batches for polymers, mass coloring are concentrates that transform thermoplastic and thermoset polymers from colorless and opaque materials to brilliant and colored. The craft of polymer coloring is not only a matter of knowing the basics of the color's perception, optical phenomena, but also understanding the reactions that pigments and dyes can have with base resin, mineral fillers and additives, as well as the material final application and the process undertaken. There are soluble colorant substances, which we call dyes, and insoluble substances, which are pigments, that can be organic or inorganic, natural or synthetic. Combinations of these type of ingredients are contained in the modern master batches, along with other non-coloring additives. It is through this complexity that it's possible to develop strength, depth, and resistance to colors. So let's discuss the properties of processing of pigment master batch. High concentration for a high coverage capacity with low impact on the polymer's properties. Uniform distribution for high throughput processes. Easy dosing for process automation. Stability at process conditions. Stability at employment conditions. Transparency or opacity based on request, possibility to create special effects such as fluorescence, opalescence, glittering, etc., and the absence of heavy metals or harmful ingredients for the manufacturing of articles in contact with food, potable water, or medical devices, etc. Among the different coloring technologies available to process polymers, Mexico iodide colors can supply master batches in granules, pastes, liquids, and pre-dispersed powders. In all of these four cases, the dispersion of different components is obtained at high shear by using available technologies to process the polymers. Another important aspect is the color matching, mainly obtained by preparing a countertype on customer's request and by imitating from the reference color table, either RAL or Pantone usually, or transferring one color from one material to another. What is pigment master batch used for? So there's color and conductive master batches, VMQ, HCR, LSR, and RTV, coloring solutions for any silicone rubber application for extrusion, molding, and calendaring, customized and ready-to-go solution in compliance with the international standards in order to achieve every customer need. And then we have color master batches for thermoset and thermoplastic, which are a wide range of master batch for extrusion and molding suitable for EPDM, MBR, SBR, FKM, etc., with tailor-made solution to better meet the request of the market. A broad range of additives master batch for a complete solution set. And we have color paste and plasticizers, many other solutions for different market applications available in phthalate or phthalate-free based plasticizers. And what is an additive master batch? Well, they are ingredients pivotal for polymers' employment success. Without antioxidant additives, for example, all products made of polypropanol and polyethylene, largely used both for private and industrial purposes, would not be available. Other materials such as dispersants, additives, and process aids ensure polymer materials are processable so as to ease their transformation in all diverse formats. The mechanism that regulate degradation and stabilization accordingly, but also rheology and processing are strictly linked to the polymer, the basics of compound formulation. It is therefore necessary to understand the related physical, chemical phenomena to calculate the reaction likely to happen by adding any additive. A plasticizer, for example, can affect the transformation process and also the article's tribological properties. The same as stabilizing additive can affect mechanical properties, electrical and thermal conductivity. Different additives can also produce synergetic effects. So the properties and processing of additive master batch, we have mechanical properties, thermal resistance, light resistance, ozone resistance, flame resistance and self-extinguishing properties, the rheology, thermoelectrical conductivity, specific gravity, resistance to fungi and bacteria, and traceability. Additives for thermoplastic and thermoset materials are formulated using a technology suitable for the processing of the carrier polymer. Additives are generally supplied in granules and can be used both during the compounding or directly during the transformation phase, molding and extrusion. Additives for VMQ are supplied in HCR form. And what is additive master batch used for? It's used for such things as food films, draw rails, technical film profiles, gardening products, films for mulching, cables, O-rings, and tubes and hoses as well. So when it comes to color matching, testing or color matching rubber compounds involves comparing the color of desired compound with the actual compound produced. The most basic test is a visual check. This can be done by comparing the samples under a standardized light source. This QC check is the quickest and cheapest way to check compound color. However, the accuracy is low and you have to have physical data to show for the test. So as an example here, this outer ring is what a customer has sent that they want that rubber supplying to that color. So firstly, you would need to do some digging of what that rubber actually is. So we would do tests such as TGA, FTIR, SG, and hardness as well, and try and match the properties of that rubber. Once we got that, we would then have a base compound without any colors in, and we would start matching to that. So color meters or spectral photometers are devices used to measure color objectively. They quantify color by measuring the reflectance or transmittance of light across various wavelengths. A colorimeter, spectral photometer, can provide precise color data, including color coordinates, such as the LAB values, color difference values, and spectral data. These measurements can be compared against the desired color specifications to assess the color match. Both visual checks and spectral photometers are susceptible to the colors being different. depending on the light source. This parameter is something to consider at the very beginning of a project and should be discussed with the customer to establish what lighting conditions the compounds will be used in. The light condition most used is daylight, or on the spectrophotometer, D65, and fluorescent light, or F11. These two conditions are meant to replicate indoor and outdoor lighting conditions. So when we do decide to colour match, it must be discussed with the customer up front due to a phenomenon called metamerism, which it refers to a phenomenon in which two objects or materials appear to have a matching or identical colour under one lighting condition, but exhibit a noticeable difference in colours when viewed under different lighting conditions. In other words, metamerism occurs when the two colours, which may initially appear to match, reveal a distinct colour difference when viewed under different lighting sources or environments. The surface of the compound that is being tested also needs consideration, as the surface texture can affect the results. The glossiness or surface finish of rubber can influence how light interacts with the material. A glossy surface reflects light more evenly and produces a smooth mirror-like appearance. The texture and roughness of the rubber surface can impact colour perception. A rough or textured surface can scatter and refract light differently, causing changes in colour appearance, transparency, or opacity. Some rubber materials may have inherent transparency or translucency, allowing light to partially pass through the material. In such cases, the colour of the underlying substrate or background can influence the perceived colour of the rubber. So here's a base for colour matching, just a simple EPDM formulation with your polymer, your additives, fillers, curatives, and oil. So the first thing we would do is cure this compound and test the rheology as well. Then we would look at what the hardness of that compound is, as there's no reason to carry on trying to colour match this compound if you're not in the specification to begin with. As you can see, this compound isn't pure white to start from at the base, and it's not too dark as well to make it more difficult, as we discussed. So we have a lot of experts here for colour matching, and they sort of know where as a base to start. You've got to start somewhere. So what we decided to do to start with was to have 2 pHr of black EPDM master batch, 2 pHr of yellow, and 2 pHr of titania. Visually, when you're looking at it, might not look too far off. You can visually see it's not fully the same color though. And using our spectral photometer, we see here it being too light, and it's also here it's showing it's too red. So the ideal thing to do here would be we need to move it into the center here, probably more green. So at the second attempt, he added only a little bit of green. Obviously, you can always add to it. Once you've put it into it, you can't take it out. So 0.05 pHr of green, and we're close to the lightness that it wants to be now, but we're still a little bit off for where we want to be on the hue. So adding more to it, he adds another 0.1 pHr of green. We're still seeing relatively where we want to be in the light, but we are moving closer to our target where we want to be. Which another thing to take into consideration is you're not going to move directly across the green because it's not fully green. There's going to be possibly a little bit greeny blue, etc. And at the fourth attempt, another 0.1 pHR of green. We're where we want to be in lightness, and we are very close and happy where we are for the hue as well. If we visually look as well, it looks a lot closer to the first attempt. So as we can see with that last attempt, this is everything that we added into it, and we get a pass on the spectral photometer. So we would then relay that to the customer. Sometimes they might want to see it first before it goes into a full production batch. So we would send them a sample to see if they are happy with that color. So to summarize, the colors in the rubber industry serve purposes beyond aesthetics. They contribute to branding, safety, product differentiation, process control, and customer appeal. So for the product differentiation, in some cases, different colors are used to differentiate between product variations or specifications. Like we said, in automotive, manufacturing, rubber seals or gaskets of different colors may signify variations in material composition, performance characteristics, or size. And then there's the process monitoring and quality control. Colors can be used as indicators during the manufacturing process, and by incorporating the color changing additives or pigments, manufacturers can monitor and control critical process parameters such as curing, mixing, or molding. Deviations in color can help identify potential issues and ensure consistent quality. We will never leave fluid compounders if we weren't happy that the color matched any previous batches that were mixed. And the polymer selection needs to be taken into consideration for the compatibility, the transparency and opacity, as well as the chemical interactions are all to be considered. The type of pigment to be used also requires consideration, whether it be organic or inorganic, as well as the form of the pigment, if it's mixed into the master batch or if it's in powdered form. So thank you for listening to this presentation on color matching. I hope you find it very useful. And yes, I think that's it.
Thank you, Robert. Thank you very much for the informative presentation on the color matching of the rubber compounds. You have explained very nicely. Thank you very much. Guys, that's the end of the presentation on the color matching of the rubber compounds, and our participant of the diploma program, executive diploma program, 360 degrees, focusing on the rubber industry, technology and management. Robert has 6+ years experience in the compounding, so it's good to know about how to deal with color matching issues in the rubber compounds. Thank you, Robert, for being part of this program today.
Thank you.
Yes, they say, so if you need more information, if you'd like to get future schedules, you can always check our website, diploma.technobiz.org. Thank you all for joining this session today.